Welcome to Math, Week 8, Factoring Strategies. This is Module Math 1 on the Math Tutor Self-Study track. Today we cover 5 factoring patterns in their standard order. Greatest common factor first, then difference of squares, perfect square trinomials, sum and difference of cubes, and factoring by grouping. Factoring reverses last week's expansion, and it is the route from a polynomial to its roots. We will also cover the machine learning link to characteristic polynomials and principal component analysis eigenvalues. We have 10 practice problems at the end. Let us get started. This video is sponsored by Subthesis. Visit subthesis.com to learn more. Factoring reverses multiplication. Given a polynomial, we find the product of simpler polynomials that expands back to it. There are 5 patterns to master, and you should try them in this exact sequence. First, always check for the greatest common factor. Second, look for a difference of squares. Third, test for a perfect square trinomial. Fourth, try the sum or difference of cubes formulas. Fifth, attempt factoring by grouping for 4-term polynomials. After the patterns, we will talk about why factoring matters. It is the route from a polynomial to its roots. Then, we will cover the machine learning link to characteristic polynomials and principal component analysis eigenvalues, followed by a 10-question practice quiz and the recap. Step 1 is always the greatest common factor. Always. Before you try any other pattern, scan all terms and find the largest factor, both numerical and variable, that is shared by every term. Then pull it out in front, leaving the leftovers in parentheses. For 6x squared minus 9x, the numerical greatest common factor of 6 and 9 is 3. The variable greatest common factor is x, because x is the lowest power of x present across the 2 terms. One term has x squared, the other has x to the first, so the minimum is x. The combined greatest common factor is 3x. Pull it out. 6x squared minus 9x equals 3x times the quantity 2x minus 3. To verify, distribute back. 3x times 2x equals 6x squared. 3x times negative 3 equals negative 9x. It matches. The greatest common factor step is mechanical, but you must do it first because patterns like difference of squares are easier to spot once the obvious greatest common factor is gone. Pattern 2. Difference of squares. A squared minus b squared equals the quantity a plus b times the quantity a minus b. 2 requirements. Both terms must be perfect squares, and they must be separated by a minus sign. For x squared minus 16, a equals x since x squared is a perfect square, and b equals 4 since 16 equals 4 squared. The result is x plus 4 times x minus 4. For 4x squared minus 25, a equals 2x since 2x quantity squared equals 4x squared, and b equals 5. The result is 2x plus 5 times 2x minus 5. Critical caveat: a squared plus b squared, the sum of squares, does not factor over the real numbers. It would require imaginary numbers, which we are not using in this course. Now let us push the difference of squares pattern further with harder examples. First, 9x to the 4th minus 49y squared. Rewrite this as 3x squared, quantity squared, minus 7y, quantity squared. So a equals 3x squared and b equals 7y. The result is 3x squared plus 7y times 3x squared minus 7y. Second, x to the 4th minus 1. This is x squared, quantity squared, minus 1 squared. so it factors as x squared plus 1 times x squared minus 1. But notice that x squared minus 1 is itself a difference of squares. It factors again into x plus 1 times x minus 1. The fully factored form is x squared plus 1 times x plus 1 times x minus 1. The takeaway is always check whether your result can be factored further. A difference of squares can sometimes be applied more than once. Pattern 3. Perfect square trinomials. A squared plus or minus 2ab plus b squared factors as the quantity a plus or minus b all squared. The middle term must be exactly 2ab for the pattern to apply. That is the verification step. For x squared plus 6x plus 9, a equals x and b equals 3, since 9 equals 3 squared. Check the middle term. 2 times 1 times 3 equals 6. It matches, so the expression factors as x plus 3 quantity squared. For x squared minus 10x plus 25, a equals x and b equals 5, since 25 equals 5 squared. Check the middle. 2 times 1 times 5 equals 10. It matches, with the minus sign carried into the factor. The result is x minus 5, quantity squared. If the middle term check fails, the trinomial is not a perfect square, and you fall through to other strategies like trial factoring or the AC method, which we cover next week. Pattern 4. Sum and difference of cubes. 2 memorized formulas. A cubed plus b cubed equals the quantity a plus b times the quantity a squared minus ab plus b squared, and a cubed minus b cubed equals the quantity a minus b times the quantity a squared plus ab plus b squared. The mnemonic for the signs is this. The first factor matches the sign of the original expression. The middle term of the trinomial factor takes the opposite sign. So sum of cubes has minus inside the trinomial, and difference of cubes has plus inside. The a squared and b squared in the trinomial are always positive. A quick worked check. X cubed minus 8 equals x cubed minus 2 cubed. This is a difference of cubes with a equals x and b equals 2. The result is x minus 2 times x squared plus 2x plus 4. The first factor matches the minus sign, and the trinomial has a plus middle term with both squared parts positive. Pattern 5. Factoring by grouping. Use this when you have 4 terms and none of the previous patterns applies cleanly. The strategy is to pair the 4 terms, usually the first 2 and the last 2, and pull a common factor out of each pair such that what remains is the same binomial in both groups. Then factor that shared binomial out as a unit. For x cubed plus 2x squared plus 3x plus 6, pair as x cubed plus 2x squared, then 3x plus 6. From the first pair, pull x squared to get x squared times the quantity x plus 2. From the second pair, pull 3 to get 3 times the quantity x plus 2. Both groups now contain the binomial x plus 2. Factor it out. The result is x plus 2 times the quantity x squared plus 3. If the two binomials do not match after pulling out factors, try a different grouping or recheck your signs. A single sign error can break the match. Sometimes a single factoring pattern is not enough. You need to apply the greatest common factor first, and then use another strategy on what remains. Consider 2x cubed minus 50x. Step 1. Extract the greatest common factor. Both terms share a factor of 2x. Pulling it out gives 2x times the quantity x squared minus 25. Step 2. Examine x squared minus 25. That is a difference of squares because x squared minus 25 equals x squared minus 5 squared. Apply the pattern to get x plus 5 times x minus 5. The fully factored result is 2x times x plus 5 times x minus 5. This example shows why the greatest common factor must always come first. Without pulling out the 2x, the difference of squares pattern would have been much harder to spot. Here's a decision flow chart you can follow for any factoring problem. Start by extracting the greatest common factor. Always do this first, no matter what. Next, count the number of terms in what remains. If you have 2 terms, check for a difference of squares or a sum or difference of cubes. If you have 3 terms, check for a perfect square trinomial. If you have 4 terms, try factoring by grouping. After applying a pattern, always check whether your result can be factored further. A difference of squares inside a larger expression, or a greatest common factor you missed the first time, can sometimes be caught on a second pass. This flowchart gives you a systematic approach so you never have to guess which pattern to try. The whole point of factoring is finding roots, the values of x that make a polynomial equal to 0. If you can write p of x as the product x minus r times x minus s, then setting p of x equal to 0 becomes a product equal to 0. A product is 0 exactly when at least one factor is 0, so the roots are immediately x equals r and x equals s. Set each factor to 0 independently, and that is the whole solution. Without factoring, finding roots requires numerical methods like bisection or Newton's method, which are slower, approximate, and can miss roots. Factoring transforms equation solving into setting each factor to 0, which is a vastly simpler task. Where does factoring show up in machine learning? Anywhere you need eigenvalues. The eigenvalues of a matrix are exactly the roots of its characteristic polynomial, which means finding eigenvalues is factoring. Principal component analysis picks the directions of maximum variance in your data, and those directions are determined by the eigenvalues and eigenvectors of the covariance matrix. The math underneath is solving the determinant of A minus lambda I equals 0 for lambda. For small matrices, that determinant is a hand-factorable polynomial. The factoring patterns you learned today are the route from a covariance matrix to a principal component analysis result. More broadly, every time you set a gradient to 0 in machine learning to find a stationary point, you are solving a polynomial-like equation, and factoring is the cleanest way to do it. Now let us check your understanding. 10 questions covering the greatest common factor, the 4 other factoring patterns, and why factoring matters for finding roots. Pause after each prompt to think before the answer reveals. Before we start the quiz, here are 4 common mistakes to watch for. Mistake 1. The sum of squares trap. Students try to factor x squared plus 25 as x plus 5 times x minus 5. But that gives x squared minus 25, not plus. The sum of 2 squares does not factor over the real numbers. Mistake 2. Forgetting to extract the greatest common factor first. If you skip the greatest common factor, expressions like 2x cubed minus 50x look unfactorable, but pulling out 2x reveals x squared minus 25, a clean difference of squares. Mistake 3. Sign errors in the cubes formulas. The middle term of the trinomial factor takes the opposite sign from the original expression. Sum of cubes has a minus inside the trinomial. Difference of cubes has a plus. Mixing these up is the most common cubes mistake. Mistake 4. Stopping too early. Always check whether your factors can themselves be factored further. X to the 4th minus 1 factors into x squared plus 1 times x squared minus 1, and that second factor breaks down again into x plus 1 times x minus 1. Question 1. Factor 6x squared minus 9x. Take a moment to think about which pattern applies here. Look at the four choices and pick your answer. The answer is A. 3 times the quantity 2 times minus 3. The numerical greatest common factor of 6 and 9 is 3. The variable greatest common factor is x, the smallest power present. Combined, that gives 3 times. Pull it out to get 3 times 2 times minus 3. Choice B only pulls out the numerical 3 and leaves the variable inside. Choice C only pulls out x and leaves the numerical greatest common factor inside. Always pull out both the numerical and variable parts together. Question 2. Factor x squared minus 16. Think about which pattern fits two terms separated by a minus sign. Choose your answer. The answer is B. The quantity x plus 4 times the quantity x minus 4. This is a classic difference of squares. X squared is a perfect square. 16 is 4 squared, and they are separated by a minus sign. Apply the pattern a squared minus b squared equals a plus b times a minus b. Choice A. X minus 4 quantity squared would expand to x squared minus 8x plus 16, not x squared minus 16. Question 3. Factor x squared plus 6x plus 9. Check whether the middle term fits the perfect square trinomial pattern. Choose your answer. The answer is A, the quantity x plus 3 squared. This is a perfect square trinomial. A equals x and b equals 3, since 9 equals 3 squared. The middle term check is 2 times 1 times 3, which equals 6. It matches. So the result is x plus 3 quantity squared. Choice C. X plus 3 times x minus 3 is the difference of squares pattern, which would give x squared minus 9, not x squared plus 6x plus 9. Question 4. Factor x cubed minus 8. Think about which perfect cube 8 represents. Choose your answer. The answer is A. The quantity x minus 2 times the quantity x squared plus 2x plus 4. This is a difference of cubes. X cubed minus 8 equals x cubed minus 2 cubed. Apply the formula with a equals x and b equals 2. The first factor matches the minus sign, giving x minus 2. The trinomial factor has the opposite sign on the middle term, giving x squared plus 2x plus 4. Choice B has the wrong sign on the middle term of the trinomial. Remember, difference of cubes puts a plus in the trinomial middle. Question 5. Factor x cubed plus 2x squared plus 3x plus 6. Notice that this expression has 4 terms. Choose your answer. The answer is A. The quantity x plus 2 times the quantity x squared plus 3. This is factoring by grouping. Pair the first two terms and the last two terms. From x cubed plus 2x squared, pull out x squared to get x squared times x plus 2. From 3x plus 6, pull out 3 to get 3 times x plus 2. Both pairs share the binomial x plus 2. Factor it out to get x plus 2 times x squared plus 3. Question 6. Factor 4x squared minus 25. Look at the structure of these two terms. Choose your answer. The answer is B. The quantity 2x plus 5 times the quantity 2x minus 5. This is a difference of squares. Recognize that 4x squared equals 2x quantity squared, and 25 equals 5 squared. Apply the pattern with a equals 2x and b equals 5. The key insight is recognizing 2x as a single unit that is being squared. Question 7. Factor x squared plus 25. Think carefully about what the plus sign means here. Choose your answer. The answer is D, cannot be factored over the real numbers. This is the sum of squares trap. X squared plus 25 has a plus sign between two perfect squares, not a minus sign. The difference of squares pattern requires subtraction. The sum of two squares does not factor using real numbers. It would require imaginary numbers, which are outside the scope of this course. This is one of the most important traps to recognize. Question 8. Factor x cubed plus 27. Identify which perfect cube 27 represents. Choose your answer. The answer is A. The quantity x plus 3 times the quantity x squared minus 3x plus 9. This is a sum of cubes. X cubed plus 27 equals x cubed plus 3 cubed. Apply the formula with a equals x and b equals 3. The first factor matches the plus sign, giving x plus 3. The trinomial has the opposite sign on the middle term, giving x squared minus 3x plus 9. Remember, sum of cubes puts a minus in the trinomial middle. Question 9. Factor 12x cubed minus 18x squared. Start by finding the greatest common factor. Choose your answer. The answer is A. 6x squared times the quantity 2x minus 3. The numerical greatest common factor of 12 and 18 is 6. The variable greatest common factor is x squared, since x squared is the lowest power of x present. Combined, the greatest common factor is 6x squared. Pull it out. 12x cubed divided by 6x squared is 2x. 18x squared divided by 6x squared is 3. The result is 6x squared times 2x minus 3. Choice B only pulls out 6x instead of 6x squared, leaving an incomplete factoring. Choice C only pulls out 3x squared, missing half the numerical greatest common factor. Question 10. Factor x squared minus 10x plus 25. Check the middle term against the perfect square trinomial test. Choose your answer. The answer is A, the quantity x minus 5 squared. This is a perfect square trinomial. A equals x and b equals 5, since 25 equals 5 squared. The middle term check is 2 times 1 times 5, which equals 10. It matches, and the minus sign carries into the factor, giving x minus 5 quantity squared. That wraps up our quiz. Let us move to the recap. A quick recap of Week 8. You drilled 5 factoring strategies. Greatest common factor extraction, which always comes first. Difference of squares. Perfect square trinomials. Sum and difference of cubes. And factoring by grouping. 3 trap families came up. The partial greatest common factor trap, where you pull only the numerical part or only the variable part instead of both. The pattern confusion trap, where you mix up difference of squares with perfect square trinomials. And the sum of squares trap, where you try to factor a sum of squares over the real numbers. Each outcome maps forward. Every quadratic next week starts with a greatest common factor check. Every characteristic polynomial in linear algebra terminates in a factoring step. Every gradient set to 0 in machine learning is a factoring problem in disguise. Coming up next. Next week applies these patterns to quadratics specifically. You will factor monic quadratics, those with leading coefficient 1, by inspection. You will handle non-monic quadratics with a leading coefficient greater than 1 using the AC method, a systematic technique that beats guessing. You will also meet the discriminant, b squared minus 4ac, and connect it to the geometry of where parabolas hit the x-axis. The discriminant classifies whether roots are rational, irrational, or complex. See you next week. That wraps up week 8. You can now apply 5 factoring strategies in their standard order. Recognize when each pattern fits, and connect factoring back to roots, eigenvalues in machine learning, and stationary points of lost surfaces. If this helped, please like and subscribe. It tells the algorithm to put this in front of more learners. See you next week for Factoring Quadratics. Sponsored by Subthesis. Visit subthesis.com.